Hi, welcome back to NCRT class 10th chapter number 13 Magnetic Effects of Electric Current. Children, in today's class, we will discuss about one more new topic called force on a current carrying conductor. See children, in the previous class we learned how the pattern according to the different shapes of the conductor will learn, isn't it? That is, suppose if the conductor is of a type straight conductor, straight one, then what would be the pattern of the magnetic field? Similarly, if the conductor is of a circular pattern, what is the magnetic field in that? And in case of a solenoid also, all the magnetic fields pattern we have studied in a previous class. So children, in today's class we are learning with a new concept called force on a current carrying conductor in a magnetic field. Means this concept means this topic is clearly it will gives an idea how force is exerted when a current carrying conductor if it is placed in a magnetic field. Means in what direction the force is exerting we are going to learn, because children, no, earlier, isn't it, that is this chapter first in the introduction classes or the first topic we learned that Oersted experiment, isn't it? What the scientist did, he came to know that when a current is flowing in a conductor, means it produces magnetism, isn't it children? Magnetic effect can be seen when a current flows in a conductor. This was what stated by Oersted. Then in order to confirm that, when he brought a compass near to that, the needle of the compass, what it made, it started deflecting, isn't it children? Why it did so? Because there is some force exerted on the needle. Because of that, it started deflection. In the same way, one more scientist called Andre Mary Ampere was a French scientist during the period 1775 to 1836. In this period, he found that a magnet also exerts a force, that is, a magnet exerts a force equal and opposite on a current carrying conductor when it is placed in a magnetic field. He stated that even a magnet exerts a force when it is placed in a magnetic field. When the current is flowing in the conductor, means it exerts a magnetism, and because of the flow of a current and a magnetic field, force can be absorbed, isn't it children? So in order to understand the direction of the force, isn't it children, in what direction the force is generated, that is exerted or produced, we want to perform a simple activity children. This is what a simple setup we want to make in order to understand this. The simple things we need children, stand we want, then the connecting words, two connecting words, this long line indicates over here, this is what wire children. Then an aluminium rod nearly 5 centimeter in length we need to take. Then after that, a horseshoe magnet we need to use, isn't it children? This is what already we know. What is this shape? Horseshoe magnet, isn't it children? Horseshoe magnet we want. And this is what? Rod, aluminium rod, isn't it children? Then we want a battery and a plug key. So after all making this setup, isn't it children, means after all taking these materials we want to connect, means we want to make a simple setup as shown in the figure. Sorry. Then how to perform this setup? Okay, I will tell you children. First, what we have to do, we have to take a aluminium rod, as I told you, around 5 centimeter length we need to take, and we should connect its both ends. This A and B represent what children? The two ends of the rod. Understanding children? Here the points A and B is nothing but the end points of the aluminium rod. These two ends are connected by the two wires, and it is suspended what? To the stand. Isn't it, children? Understanding? The aluminum rod, with the help of the two connecting wires, it got suspended with the, that is from the stand. Means it is just hanged over the stand. Okay, after doing, means after hanging this rod, what is the next step, children? We should bring a horseshoe magnet, a powerful horseshoe magnet we should bring near to the aluminum rod. And this horseshoe magnet should be kept in a way that the magnetic field, understanding, children, the horseshoe magnet should be placed in such a way that the magnetic field should be directed upwards. Understanding, children? Initially what we are doing, the magnetic field is directed upwards. Isn't it, children? This arrow indicates what? Upward direction. And the two end points of the magnet, isn't it, children? Every magnet have a two ends. Here also the horseshoe magnet have a two end points, isn't it? Those are named as a S and N. S means south end point, N means here north end point. And in such a way that the north pole of the horseshoe magnet should lie. Understanding, children? This north pole of the magnet should be vertically below the rod. This is what rod? To this rod, the north pole should be below. And got it, children? Whereas the south pole of the magnet should be vertically above. Got it? How the magnetic poles should be? Initially, the north pole should lie, that is below the rod, whereas the south pole should lie above the rod. Okay. Now, after connecting, so we need to connect all the aluminum rod in series with the battery and a plug key and a rheostat. Isn't it, children? We should make a series connection. Then what we have to do after all making this setup, we should allow the flow of a current from the point B to point A. We should pass the current. Isn't it, children? In what direction? We are passing the current in this direction. See, you can look at this. This positive terminal indicates what here? That is flow of a current in this direction. So, initially the current is moving. Isn't it, children? Initially, how the current will move? That is, initially current is flowing from end point B to A. Got it, children, my point? When the current starts moving in this direction, means from the point B to point A, we need to observe the rod now. The very important step what we have to do, we have to observe what the changes are occurring on the rod. It has been experimentally found that, children, when the current starts flowing from a point B to point A, the rod gets displaced towards left side. Got it, children, my point? When the current starts flowing from B to A, the rod gets displaced towards left. Got it? This is very important, children. When the current starts moving in this direction, means it is flowing from point B to point A, this rod has shown displacement. Means it started little bit moving, isn't it? Just moving or displacing what? Towards left, isn't it? This is what one case we have observed. Now we have to go for reversing the connection. If we want to change the direction of the flow of the current, means what we have to do? We need to change the terminals. The positive terminal should be now what here? Negative, and the previous negative will become now positive, isn't it? At the second case, suppose if current is flowing from, because if now it has become this side positive and this side is what, negative. Always the current will move opposite to the direction of an electrons, isn't it children? When the current starts moving in this direction, now the current is moving in this direction now, then what, the through this wire it starts moving in this way, means A to B it will goes, and here to again it will come back to the battery. So when the current starts moving from point A to B, got it children my point? We need to observe again the change in the rod. It has been experimentally found that children, when the current starts moving or flowing from point A to B, the rod gets displaced towards right. How it got displaced children? The rod gets displaced towards which direction? Right side. Isn't it children? These two are the main things we have understand. Means we found that when the current is flowing from end B to end A, the displacement of the rod is towards left. When we reverse the flow of a direction of a current, there is also change in the direction of a force. Isn't it children? Because of that force, the rod now displaced towards right. So this actually displacement, what this displacement indicates here, the displacement of a rod is nothing but the force exerted on a current carrying conductor children. See, this is what now, this rod is nothing but now conductor. To this conductor we are supplying energy, means we are passing current. Isn't it children? Now once if a conductor carries current, means what it will produce is magnetic effect. Isn't it children? So here magnetism has produced, magnetic field has generated. Isn't it children? And when there is the magnetic field, means it should be there what? Force there also. Isn't it? Because of that force, the rod get displaced. Simple children. Isn't it? And here one more thing we have understand that when there is a change of there is reversal of a current, flow of a current, that is when we change the direction of a current in this setup, we have observed that the direction of the force also get reversed. Simple, no children? It's quite, yes. So once again I'll repeat children, by using the aluminum rod and a horseshoe magnet, if we connect in this way, when the current starts flowing initially from point B to point A, the rod has shown displacement towards left hand side. And when we change the flow of a direction of a current reverse, that is when we change this direction, means it has observed that the displacement of the rod also changed. It has initially it has displaced towards left, now it is displacing towards right. Means from this activity we can conclude that there is an equal and opposite force on a current carrying conductor. Got it children my point? And also we can do, that is the same setup, if the magnetic field is directed now downwards. Isn't it children? When we change the polarities of the magnets, it will become now the magnetic field downwards. And if we observe in that also, the direction of a force is going to change according to the change in the direction of the flow of a current. Means one very important thing we have confirmed with this activity, that the direction of a force is related to the direction of a current as well as the magnetic field. And moreover children, it has found that the direction of the force is highest or largest when it is perpendicular, means right angles to the direction of a flow of a current and direction of a flow, that is magnetic field. Understanding children? That is force is greater, the force is will become greater, force is highest or largest when children, that is when it is perpendicular to current and magnetic field. Isn't it, children? So, in order to find the direction of a force, in which direction we want to know, no? We are telling that the force has exerted here and the rod has shown displacement. Means, in order to find the direction here, we need to use a simple rule called Fleming's left hand rule. Got it, children? That Fleming's left hand rule we will discuss in the next video. First you understand this concept clearly, children. This activity clearly explains us when a current carrying conductor is placed in a magnetic field. See, this is a magnet, isn't it? A horseshoe magnet is a powerful one. This is one magnet, and now when current, if we pass to this rod, means it also becomes magnet, isn't it, children? Because of these two powerful magnets, a force has generated, and because of this force, the displacement is absorbed here, isn't it? And this force will becomes, that is, largest or highest when it is perpendicular or right angles to the flow of a direction of a current and as well as to the direction of a magnetic field. Got it, children? So, children, we can say that the force produced on a current carrying conductor mainly depends upon two things, isn't it, children? That is, the displacement of the rod is largest when it is perpendicular to current and magnetic field, isn't it, children? And suppose if the length of the rod increases, means the displacement also increases, isn't it? It also depends upon length. If length of rod increases, means the displacement also increases, isn't it? Increases means displacement also increases. And suppose if the flow of a current increases, means displacement also increases. That is, displacement of the rod also increases. So, increases. So, these 2 points you remember, children, isn't it, children? How can we increase the displacement of the rod? Means by increasing the length of the rod we can increase the displacement, and similarly when we increase the flow of a current across it we can increase the displacement over here. Got it, children?